started on today's notes over making conjectures using inductive reasoning. First, let's talk about some vocabulary. What is inductive reasoning? Inductive reasoning is using a pattern to draw a conclusion. And that conclusion is called a conjecture. A conjecture is a conclusion made by guessing. It's not accepted as fact. It's more of an educated guess. So let's talk about the process of inductive reasoning. When we conclude a statement is believed to be true, it is called a conjecture. So remember, it's believed to be true. We're not saying this is absolutely true. It's just believed to be true. We form this conjecture after observing specific cases and finding a pattern. So I've got the process on the left and a very basic example on the right. So this right here is the process of inductive reasoning. Let's write that down. The process of inductive reasoning. And over here, I've got a very basic example. So the first thing you're going to do in the inductive reasoning process is you're going to make observations from specific cases. So specific is the key word, and you're just making observations. So in our specific cases that we have over here, specific cases, you always leave for school by 7:30 a.m. Okay, those are just observations that you've made. You leave for school by 7:30 a.m. every day. The next step in the process is you look for a pattern. That's very big in inductive reasoning. You look for a pattern. So something that you notice is you are always on time for school. So here you have a pattern of being on time. Observation, you leave for school by 7:30 a.m. Pattern, you're always on time for school. After that, you form a conjecture. Remember, this is just a conclusion based on the specific cases. So my conclusion is, or my conjecture based on these observations and the patterns that I've noticed, if you leave for school by 7:30 a.m., you will be on time. So that's a very basic example of the inductive reasoning process. So let's practice the first part of it, identifying a pattern. In these three examples, we're going to identify a pattern and we're going to find the next item in the pattern. So in number 1, 5, 10, 15, 20, 25, what's the next item in the pattern? It's going to be 30. The pattern is we're counting by fives. In number 2, I've got a die in each item. The first one has 1 dot. The second has 2. The third has 3. The fourth has 4. So what is the next one going to have? It's going to have 5 dots. So let's draw that. 1, 2, 3, 4, 5. So we're just identifying a pattern and we're finding the next item. In number 3, we've got arrows. The first is pointed to the right. The next one looks like it's rotated 90 degrees clockwise, pointing down. Then it's rotated another 90 degrees clockwise, pointing left. So if I rotated it another 90 degrees clockwise, it should be facing up. That's the next item. In part 2, we're going to make a conjecture. So in the first part, examples 1 through 3, we just identified a pattern. Now we're going to make a conjecture, and it says complete each conjecture. So number 4 says the product of 2 even numbers is, okay, well, if I'm going to complete this conjecture, I need to list some examples and identify a pattern. So let's list some examples. Well, 2 even numbers. So let's do 2 times 4. What is 2 times 4? Those are 2 even numbers. The product is 8. Let's list another example. 2 even numbers. We could use 6 and 10. 6 times 10, the product is 60. Let's list another example. 8 and 12, those are even numbers, right? 8 times 12, what is 8 times 12? It's 96. Let's list another example. Maybe 30 and 6. 30 times 6 is 180. Let's list another example. 2 and 8. 2 times 8 is 16. So what do you notice about the product of two even numbers? They're all even. All of these numbers, 8, 60, 96, 180, and 16, those are all even numbers. Now over here, it says list examples and look for a pattern. Be sure to use different types of numbers, i.e., whole numbers, fractions, decimals, negative numbers. In this case, it was specific. We needed two even numbers. But in other examples, you might want to use fractions, decimals, negative numbers. Let's move on to number 5. If a polygon has n sides, then there are blank triangles formed when diagonals are drawn from any vertex of the polygon. Okay, so I'm going to explain what some of these vocabulary words that you may not know are. So if a polygon has n sides, there are blank triangles formed when diagonals are drawn from any vertex of the polygon. Okay, well, let's start with a triangle. How many sides does a triangle have? 3 sides. How many triangles do I have? I have 1 triangle. Just 1. Let's draw a quadrilateral. Okay, so if I'm going to draw a diagonal, I'm going to draw it from one vertex to another. Obviously, these 2 vertices are already connected. These 2 vertices are already connected. I'm going to draw it across right there. Okay, so I have 4 sides in this polygon. How many triangles are formed when I draw diagonals? 1, 2. So 4 sides, 2 triangles. Do you see what we're doing here? Let's draw a pentagon. I'm going to draw like a house. Okay, there we go. There's my 5-sided figure. Okay, so that's a pentagon. It's got how many sides? It's got 5 sides. Now let's draw some diagonals. So basically, I'm breaking this polygon up into like how many triangles can I form based on diagonals that I've drawn. So from here to here, and maybe from here to here. I have 1, 2, 3 triangles. Oh, I need to do that. I'm going to write 3 triangles. Okay, let's draw a hexagon now. Let's see, 1, 2, 3, 4, 5, 6. Oh my gosh, that is super ugly, but that's okay. It doesn't have to be perfect. And now let's draw some diagonals. So maybe from here to here. And look, I can draw it from here to here. I can draw it from here to here because it says from any vertex of the polygon. So I have a 6-sided figure, which is a hexagon. How many triangles are formed from the diagonals that I've drawn? 1, 2, 3, 4. 4 triangles. Okay, so we've drawn some examples, right? Because it's okay. We can list examples like we did in number 4, and then we can draw examples like we've done in number 5. After we've drawn examples, now we need to identify a pattern. What do you notice about the relationship between the number of sides and number of triangles? And let's write that down. What do you notice? Because you want to be able to refer to this, right? What do you notice about the relationship between the number of sides and number of triangles? The number of sides and number of triangles. What do you notice about the relationship? Well, if I have n, which is, what does n represent? N represents the number of sides. What do you notice about the number of sides and number of triangles? How many triangles are formed? N minus 2, right? If I have 3 sides, 1 triangle. 4 sides, 2 triangles. 5 sides, 3 triangles. 6 sides, 4 triangles. So n minus 2 is the number of triangles, right? That expression represents the number of triangles. And I'm going to write that down, okay? Let's move on to number 6. If the side length of a square is doubled, The perimeter of the square is blank. So we're talking about the side length of a square. We're going to double it each time. The perimeter of the square, okay, that's the outsides added together, right? The distance around a figure. Well, what if I have a square that's 1 on each side, okay? 1 on each side, what's the perimeter? 4. What if I double that? So now the side length is going to be 2. What's the perimeter of a square that has a side length of 2? 8. What if I double that? So I get 4 on each side. If the perimeter is, the side length is 4, what's the perimeter of the square? 16. What if I double that? The side length of the square is 8. What's the perimeter of the square? It's 32. So what do you notice? If the side length of a square is doubled, what's the pattern? It's also doubled, right? 4 doubled is 8. I double 8, I get 16. I double 16, I get 32. So that's my conjecture. I completed it. If the side length of a square is doubled, the perimeter of the square is doubled. Okay, so we've talked about the inductive reasoning process of observing specific cases, identifying a pattern, and then forming a conjecture. But remember that conjecture is not to be accepted as fact, okay? We can always find a counterexample, and a counterexample is an example in which the conjecture is not true. So we can prove that conjectures are false, because remember, they're just educated guesses. To show that conjectures are always true, you must prove it. But to show that they are false, you must find only one counterexample. A counterexample can be a statement, a drawing, or a number. So let's move on to number 7. This is part 3 of our notes, and it's finding a counterexample. So in number 7, for any real number x, x squared is greater than or equal to x. So let's list some numbers, right? Because we've got to write some specific cases and see if we can identify a pattern and maybe find an example where this conjecture is false. Well, let's try the number 4. And I'm going to write this out. 4 squared is greater than or equal to 4, right? Because that's my conjecture. X squared is greater than or equal to x. So if x is 4, 4 squared is greater than or equal to 4. Well, what is 4 squared? It's 16. And 16 is greater than or equal to 4, so that is true. Let's try another example. Let's try 10. Okay, so that means 10 squared is greater than or equal to 10. What is 10 squared? It's 100, and 100 is in fact greater than or equal to 10. So that's another example where this statement is true. This conjecture is true. Well, remember, our notes on the last page said to list numbers that are positive, negative, fractions, decimals. So let's try a negative number. Well, what if x is negative 3? Well, negative 3 squared is greater than or equal to negative 3. And what is negative 3 squared? It's 9, and 9 is greater than or equal to negative 3. So that's true, okay? Well, let's try 0, because 0 is kind of different, right? So 0 squared is 0 squared greater than or equal to 0. Well, 0 squared is 0, and 0 is greater than or equal to 0. Okay. All right, well, let's move on to another type of number. Let's try a fraction. 1/2. Is 1/2 squared greater than or equal to 1/2? Remember, 1/2 squared is 1/2 times 1/2. And when we multiply fractions, we multiply across. So I get 1 over 2 times 2, which is 4. So 1/2 squared is 1/4. Is 1/4 greater than or equal to 1/2? It is not. This is my counterexample. Right here, this is my counterexample. So if x is a proper fraction, the conjecture is false. And let's write that down. If x is a proper fraction, which what does that mean? That means my numerator is smaller than my denominator. If x is a proper fraction, the conjecture is false. False. So we just found a counterexample. Let's move on to number 8. The number of moons orbiting each planet in our solar system does not exceed 27 moons. That's the conjecture. Information in the table to the right was gathered from science.nasa.org, and it has the planets listed with the number of moons for each planet. What's my counterexample? Well, Jupiter has 95 moons and Saturn has 146 moons. Let's write that down. Jupiter has 95 moons and Saturn has 146 moons. Therefore, right, I love this symbol, therefore, the conjecture is false. There's our counterexample. We identified it in the table. Okay, so let's recap. Let's talk about the inductive reasoning process. So the first step in the inductive reasoning process is to what? We are going to observe specific cases. And so I'm going to write this process and I'm going to give like a little example. So our example is that we observe several species of birds and notice they all have wings. That's our observation. So let's write that down. We observe several species. Oh my gosh, sorry. Whoop. Several species of birds and notice they all have wings. Okay, I'm writing fast, and that's why my handwriting is so messy, but we're moving on. So observe specific cases. The next step in the process is to identify a pattern. So again, this is the process, and this is just a little example. So the pattern that we notice is the birds with wings can fly. That's just something that we noticed with all the birds that we observed. So several species of birds, and notice they all have wings. All the species of birds that we see all have wings, and the birds with wings can fly. That's the pattern that we notice. The next step in the process is you form a conjecture based on the pattern recognized from specific cases observed. So let's write that down. We form a conjecture based on the pattern recognized from specific cases observed. Okay, so the conjecture that we're going to form is that all birds with wings can fly. Okay, so that's the conjecture that we're forming. All birds with wings can fly. That's our conjecture. Okay? Okay, so then we've observed, we found a pattern, we formed a conjecture. Is it true? If yes, we have to prove it. We have to prove it. If no, we need to find at least one counterexample. Only one, though. So I said at least one, but you only need one. You need to find at least one counterexample. Remember, that is an example where the conjecture is not true, but you only need one. So in this case, we know that not all birds with wings can fly because penguins have wings and they cannot fly. So that's our example here. We're going to say it's false. Penguins have wings and cannot fly. So this is just your graphic organizer that we've used to just kind of go over the process of inductive reasoning. But this concludes your notes over making conjectures using inductive reasoning. I hope it was helpful.